Because we're running behind, I decided to make a video to go over the questions and problems that you worked on in class today. So you'll get to see the correct answers, just we won't take class time to do it. All right, so our first question. We have two conductors. They're insulated from each other, so they make a capacitor. The idea that's implied is they start off with a charge of Q and minus Q, and we're going to increase this to 2Q and to minus 2Q. And the question is, what's going to happen to the capacitance? Does it change? The important thing about this question is that we're keeping the conductors in the same positions. Remember that I told you that the capacitance is defined or determined by how the capacitor is put together. So because we're not changing anything about how it's been put together, the capacitance has to remain the same. How does that work? Well, if you think about it, by increasing the charge on the conductors, we're going to increase the electric field between the two plates. It's going to get stronger because of more charge. This also will mean that the potential difference across the plates will increase as well. In fact, what's going to happen is the charge is going to double. The potential difference will also double, and you can see that the ratio remains the same. Now, this problem is a little bit different. We're going to reposition the two plates of the capacitor so the capacitance doubles. There's a vacuum between the plates, which doesn't mean much because we haven't talked about dielectrics yet, but it will. If you keep the charges the same, what happens to the potential difference between the plates? So we're told that the plates are going to move so that the capacitance doubles and Q is not going to change. So if, keeping in mind that capacitance is charge over voltage, if we have this go to 2C, but the Q is not going to change, the only thing that could change would be the potential difference. We would need the potential difference to be half as big in order to get the capacitance to double. And so that becomes our answer, because the 1/2 on the bottom, of course, the 2 will flip onto top and we'll get 2Q over V. All right, now here is a problem. This is a parallel plate capacitor. We know the area of the plates and the separation. Okay, so this deals with the expression that we introduced during the lecture of how we would calculate the capacitance of a parallel plate capacitor if we know the dimensions of the plates. The area is given to us, and D represents the separation between the plates. Epsilon naught is our constant. Our area is 1 meter squared. Our separation is 1 millimeter. We need to change that to meters. And this gives us a capacitance of 8.85 times 10 to the minus 9, which we could call 8.85 nanofarads. In part B, we want to know how much charge is stored in this capacitor. If it has a voltage of 3 times 10 to the third volts, that's 3,000 volts. That's going to use a different expression for capacitance, where we say Q over V. We can rearrange this, and Q is C times V. So we have 8.85 times 10 to the minus 9 times the 3 times 10 to the third. And this gives us 2.655 times 10 to the minus 5 coulombs, which I could write if I wanted to, but I don't have to. 26.55 microcoulombs. So that was a pretty straightforward problem. That was just extra area to work. Okay, so now we have some questions about capacitors in series and in parallel. The parallels coming up. These two capacitors that we see in this picture are connected in series because the wire just goes from one capacitor into the next. There's no splitting into branches that we would have with parallel plate capacitors. Parallel capacitors in parallel. All right, so we want to know what the equivalent capacitance of these are. So when they're in series, we add the reciprocals, 1/12 plus 1/6. These numbers are nice. I could just do a common denominator. So 3/12 could be reduced to 1/4. So the equivalent is the reciprocal of 1/4, which would be 4. And that's in microfarads. Notice I don't have to put the 10 to the minus 6 in the denominator. I can just put the units in at the end. So my equivalent is 4 microfarads. All right, now we've connected the two capacitors in parallel because you can see that the wire splits and then it comes back together after them. So these two are in parallel. We're told that the charge on the 6 microfarad capacitor is 24 microcoulombs. And it turns out that when capacitors are connected in parallel, they have the same voltage. They don't have the same charge. So we can figure out, if I use the expression for capacitance, I can rearrange it. And we can figure out what the voltage is on this capacitor. It's going to be 24 microcoulombs over 6 microfarads, so it's 4 volts. So that this is also at 4 volts because they're in parallel. And then the charge was just multiply the voltage times the capacitance, and I get 48 microcoulombs for the charge on the 12 microfarad capacitor. All right, now we're back to the two capacitors in series. We're told the charge on the 12 microfarad capacitor is 24 microcoulombs. Turns out because they're in series, they have the same charge, so I'm just going to write that down. And we're asked to find the potential across the 6 microfarad capacitor. Well, now I've made it easy for myself. The voltage is going to be Q over C, which is going to be 24 microcoulombs over 6 microfarads, and that's going to be 4 volts. Now here's a problem where I'm going to be simplifying a circuit. I'm just going to put in the values for capacitance. This is 12 microfarads. This is 2 microfarads, and this is 4 microfarads. All right, the first thing that I'm going to tackle is I'm going to look at these two because they're in parallel. I'm going to find the equivalent for those, which is just simply found by adding them. And then I will redraw this. Now I've simplified it to 2 in series. One is 12 microfarads and the other one is the one I just found is 6 microfarads. My battery's 12 volts. And now I'm going to do these two are in series. I'll take 1/12 plus 1/6 is 1 over the equivalent. So the equivalent here is just 4 microfarads. So my final result is the equivalent to all three of those is one capacitor of 4 microfarads attached to my 12-volt battery. And now I'm going to start to go back to give more information. The voltage across this is 12 volts. Its charge is 48 microcoulombs. Now when I go back to here, both of these are in series. They have the same charge, so it's 48 microcoulombs. And then I can use that to find the voltage across each of them, which is going to be the charge divided by the capacitance. So this one is going to be 4 volts. This one's going to be 8 volts. Notice that 8 plus 4 adds up to be 12. All makes sense. And then the 6 microfarad capacitor is in place of these two that are in parallel. So I know that the potential across that one, which is 8 volts, is also the potential across these, which is then gives me my charge is going to be 32 microcoulombs, and this one is 16 microcoulombs, and 32 and 16 add up to be 48. So that is going to be that problem. All right. Now we're going to do some work with energy. So remember, there's a couple different relationships I can use for energy. I like 1/2 CV squared is one of the expressions, and I'm just going to see if I can use this. We're told that the voltage across a given parallel plate capacitor is doubled. How is the energy stored in the capacitor affected? Okay, so we put more. The voltage is going to go to twice the voltage, but we have to ask ourselves, was the capacitance changing? We don't see anything about changing the geometry of the capacitor, so that's not going to change. So U initial is just using the original values, but our new value of energy is 1/2 C, but I'm going to take twice the voltage and square it, so I'm going to get 4 times 1/2 CV squared. So what we've seen is that the energy actually increased by a factor of 4. I want to connect a 12 microfarad capacitor and a 4 and a 6 microfarad capacitor, and it wants to know if I should connect them so that when the capacitors are charged, the 12 microfarad capacitor will have a greater amount of stored energy than the 6 microfarad capacitor. So I'm going to look at what would be the effect if they were in parallel. If they're in parallel, the V would be the same for both of them. And so the energy would be 1/2 CV squared. Because the voltage would be the same for both of those, the capacitor that would have the greatest value would also have more energy because it's bigger. Okay, so I showed when they're in parallel, the 12 microfarad has more energy. So just to double check, in case what happens in series? Let's think about that. Just to be sure, that maybe it's both ways, maybe it doesn't matter. So let's imagine the two are connected in series, and just because I know they have the same charge, I'm just going to give them 24 microcoulombs because I know they have to have the same charge. And that's a nice number that's going to divide nicely. Using the relationship between capacitance, charge, and voltage, the voltage can be found by taking Q over C. So the voltage across the 12 microfarad will be 2 volts, and the voltage across the 6 microfarad one will be 4 volts. So now if I do U equals 1/2 CV squared, I get 1/2 times 12 times 2 squared, which is just going to be 6 times 4 is 24, and that's for the 12. U for the 6 is going to be 1/2 times 6 times 4 squared. That's going to be 3 times 16, and that's 48. So when they're connected in series, this one has more energy. So the way that I can connect them so that the 12 microfarad capacitor has more energy is to connect them in parallel. And finally, it asked me to find the energy stored in this capacitor network when the capacitors are fully charged and when the capacitance is. These are the values that I worked with before in the problem from a few slides ago. And I wanted to just remind you that when I broke this down, I actually simplified it into the 12-volt battery. And the overall equivalent capacitance was 4 microfarads. And so if I wanted to express the energy of this, would be 1/2 CV squared. So 1/2 times the 4 microfarads times V squared, which is 12 squared. I will use times 10 to the minus 6 here. And this is going to be 2 times 10 to the minus 6 times 144, which is going to be 288 times 10 to the minus 6 joules. And that would be the total energy. I should be able to work back and find the energy of each of them individually. And if I did them each individually, I should also see if I add them all up, I should get the same total amount of energy. And that's it.